Log on, tune in, find out. Another good idea from Cambridge.
Is Luisa Bonet from the Universitat Politècnica de Catalunya, Spain, and she's going to talk about some interesting work they've been doing on unrooted SPR, which is a computational problem that has lots of interesting and rather difficult combinatorial aspects.
Well, this is Jordan Margaret. We can't hear you. Okay. Because I didn't turn it on. Can you hear me now?
Better.
I really don't know if this is this working? No, I don't. That's okay. Okay, I'll try to scream a little bit,
Maybe the technical person could make it louder.
I need your voice on tape anyways. No. And I turned it on. I turned it on as he said. He didn't say that I should do anything else. No.
Yeah, probably best just to start, and I'll try and.
Okay. So, as I said, this is joint work with Catherine St. John, and it was published last year in DCBB. Okay. So basically, what we want to study is the distances among trees. For instance, here we have two very similar trees that are basically, there's a small difference in this area. We want to quantify how different or what's the distance to go from one tree to the other. There are several distances defined, and they're very useful to search through tree space to find the most parsimonious tree for a set of species. So one distance that can be defined is the Robinson-Fools distance, where we are counting the branches that are in one tree and not the other one. For instance, these red edges here, so the distance would be 2. And we have linear time algorithms to find this Robinson-Fools distance. But there's other distances that are more helpful in terms of searching through tree space, like tree bisection and reconnect. And I'm going to define it because I'm going to use some ideas to work with SPR. Tree bisection and reconnect. We can define the moves as we detach. So we have a tree with species, and we remove one edge. For instance, this one. I know. Yeah. Sorry. We remove this edge. Okay. And then we attach an edge between any two nodes of the two subtrees, for instance, attaching from this edge to this edge. And we create this new tree, which is distance 1 from the original one, right? And it just consists of detaching an edge, and then you have two subtrees and attaching them however you want, okay? So the TBR distance between the two trees is the minimal number of TBR moves to go from one tree to the other one. So we know that this problem, calculating the distance, the TBR distance, is NP hard. And so now I'm going to define the SPR distance, which is the one that we're going to be working with, which is subtree prune and regraft, which is a little bit different than the TBR one in the sense that what we do is, for instance, we detach this edge and grab it, okay, and then attach this subtree to another edge in the rest of the tree. Okay. So in the previous distance, we just disconnected. We removed an edge, and then connected, two other edges. So this is a little bit different. This is like partly rooted in the sense that here is like keeping a root on this detached part. And the distance between two trees, the SPR distance between two trees is the minimal number of moves, SPR moves to transform one tree into the other tree. Okay. There's also the rooted version of this distance, okay, but in this talk, the results that I will present will be for the unrooted version of SPR distance. Also, just to say that the TBR distance between two trees is less or equal than the SPR distance between two trees. Why is that? Because an SPR move is always a TBR move. Like the TBR move is more general. To produce a TBR move, we may need two SPR moves, right? So this is also an NP-hard problem, calculating the SPR, the rooted, okay, so the first thing that was proved is that the rooted version of this distance is NP-hard to calculate. And then there were some approximation algorithms to calculate the SPR distance on rooted trees. One by me, Catherine, Amenta, and Mahindru, and then there was another one later on. Okay. So to be able to work with these distances, there's a couple of rules that help us figure out what the distances between the two trees are. The first rule, which is very simple, is the first reduction rule is the subtree rule. So suppose we have two trees, this one, and they have a common subtree exactly identical in both of them. So what we know is that we can substitute this subtree A by a new leaf and produce these two trees. Okay? What we know is that the distance of these two trees is identical to the distance of these two trees if we talk about TBR distance or SPR distance, rooted or unrooted, or hybrid number. Okay? And the next rule, the next reduction rule, is called the chain rule. And what we do is, suppose we have these two trees that have a common chain, of length, say, n, in both of them, and we can reduce the chain to a small chain of 3 leaves, okay? And for some distances, it is known that, for some types of distance, it's known that the distance between these two is exactly equal to the distance between these two, okay? So, for instance, for TBR, Allen and Steele proved that the chain rule preserves the distance. For rooted SPR, also we knew from 2004 that the distance is preserved. And, well, it's not exactly this distance. There's some small modifications, and the same for hybrid number, okay? But nothing is known, actually, for the non-rooted version of the SPR distance, okay? So this is a problem that Mike Steele posed a few years ago. And he proposed the following questions. He wanted to know if shrinking the common chains, as I showed you before, that reduction rule, if it preserves SPR distance, okay? And he was interested in that. Maybe there's other reasons, but one is a consequence is that if we can preserve the chain rule, then we know that calculating SPR distance is fixed parameter tractable. Okay, so you can find some nicer algorithms that if the distance is small, calculating the distance is tractable. Okay, I will explain this later. So, because of the other distances, not the SPR, but the TBR, the rooted SPR, etc., we know that the chain rule preserves the distance. We know that calculating these distances, is fixed parameter tractable, and I will explain what this is. So the two things that I'm gonna talk about, I don't know if I will have time to present. I will not have time to present this second result, but I will explain, a little bit. So we don't know, as I said, if for the SPR distance, when we make the chain reduction, we don't know if the distance between these two trees is smaller than the distance between these two trees. Okay. So there's the work of Hickey and others, that show that when we make the chain reduction, here this notation means that T1n, T2n is like T1 and T2 have a chain of length n, and T1, 3, T2, 3 is the reduction using the chain rule, just eliminate that n chain and substitute it by a 3 chain, okay? So what they proved is that by making this reduction, the distance between these two trees cannot be reduced more than by 2, okay? So we did a very careful analysis of cases, and we managed to say that by doing this chain rule, we can reduce the distance between these two trees one less than this distance at most, okay? And we felt that we were very close, but we cannot solve the main question that Mike posed, and whether these two distances would be the same or not. So this is still open. Hickey and others also showed that calculating this distance is NP hard. Okay, so this is one of the results that I wanted to talk about, and the other one is that calculating the SPR distance is fixed parameter tractable. So what does it mean that it's fixed parameter tractable? So suppose we use the distance parameter k, So we want to know if we can decide if the two trees have distance k, and the time to decide it would be a polynomial in the size of the input times a function in terms of k, where the complexity and possible exponential complexity of calculating the problem has moved to this function, right? And the part of and the function respect to n, which is the size of the input, is polynomial. So if we're talking about two trees that have a small distance, we can have algorithms that function in polynomial time. If k is constant, then we can have polynomial time behavior and tractable algorithms. Okay, so this is what we were looking for, and this we managed to do. Okay, to solve. But before I explain how we managed to prove that SPR distance is fixed parameter tractable, I'm going to sketch the proof of Allen and Steele of 2001, proving that TBR distance is fixed parameter tractable. Okay. So we have a pair of trees, and we want to know if they're distance apart k. This time in terms of TBR, okay, which is the first one that was proved fixed parameter tractable. So what we do is we obtain two new trees by applying the two rules, the subtree rule and the chain reduction rule, as far as we can, okay? And we get two trees, T1 prime and T2 prime, that we call them reduced, okay? And where we cannot do any more reductions. But what we know is that they have the same distance as the original trees. And we also know that the size of them has been reduced, and the size that is left, okay, is basically a constant times the initial distance between T1 and T2, okay? So what's left there accounts for the moves basically to go from T1 to T2. That's the intuition. So then how is the algorithm? The algorithm then works, okay, we look at T1 prime, which should be, if T1 and T2 have distance k, T1 should be less or equal than a constant times the distance of the original trees. So if the size of T1 prime is bigger, then we know that the distance of the original trees is bigger than k, and we answer no. Otherwise, we check all possible k TBR moves from T1 prime, from the reduced tree 1 to the reduced tree 2. okay? And since these trees are reduced and have the same distance as the original ones, okay, but now the size is in terms of k, okay, then the time that it takes to do this is, well, we have to pick any two edges from T1. For the first move, we pick any two edges from the first tree to remove and to connect, basically, you know. And so we look at all the possible first moves and so on until the kth possible move. And that since T1 prime is less than k times d, a constant, okay, so the complexity of this step is k to 2k, okay. This polynomial in n is the time that it takes to do the reductions, the subtree reduction and the chain reduction. So as we said, you know, we have behavior for calculating the TBR distance that the complexity, the exponential complexity is in terms of the k, which is the distance, rather than in terms of the sizes of the trees, okay? So we wanted to prove the same result for SPR distance, but of course we don't have this result and we didn't have this result, okay? We don't know if after applying the chain reduction we have the same distance, okay? So this is what we did. So basically we defined a chain reduction that was, you know, parameterized. This L is wrong, by the way. So it's a parameterized chain reduction. You have a common chain of length L, and you reduce it to a certain size. You can reduce it to a certain size, okay? What is the size that you can reduce the chain to? Well, this is the lemma. If you have T1 and T2, which have distance, they have distance k, okay, then you can use a chain reduction that is c times k, and then you preserve the SPR distance, okay? What is the c? The c is, okay, the number, one more than the number of edges affected by an SPR move, okay? So the idea of the proof would be, so you want to prove that this distance is the same as this distance and no less, okay? So what do you do? If these two trees had distance k, okay, and these two trees, say, had distance k minus 1, then you could only affect at most a constant number of k edges from this comb, you know, from this chain, right? So there would be a part here, something like this, that would not be affected at all by the SPR moves that take you from this tree to this tree, okay? And then you could stick inside all the leaves that are extra here, okay? And then from the set of moves that take you from this tree to this tree, you would obtain, you know, the moves to go from this tree to this tree in, say, k minus 1 distance, okay? Which would be a contradiction. Basically, the idea is that this C talks about, you know, how many edges are affected every time that we do an SPR move, and we take C one more, so that if these two trees are, say, k minus 1 distance apart, you know, then there would be a part of this comb, you know, that with two consecutive leaves, with three consecutive leaves that is not, you know, that is not touched at all. And then we could stick the extra leaves in there, okay? So this is how we change the chain rule. And then we have to do something about the other result. Oops, I'm almost out of time, right? Okay. So the other result is that, well, if you have two trees that are a distance apart k, and you reduce them as much as you can using the subtree rule and the KC, in this case, KC chain rule, then the size of the reduced trees are less or equal than a constant times k squared, okay? Basically, what we do is we reproduce the proof of Allen and Steele of 2001 for TBR, But instead of having chains of size 3, we have chains of size k. Okay? And so we get somewhat worse result, but we get something that will work for the same theorem, proving that the TBR distance is fixed parameter tractable, because what we do, I get confused by the, okay, so what we do is we take the two trees and the distance parameter given as input, we reduce the two trees using these two reductions. What we obtain are trees that have the same distance now, because we're not using the 3-chain, but we're using this parameterized chain rule. And we know that the size of the trees is at most a constant times k square. And then what we do is the same as before. We search through all possible k moves, SPR k moves, And then the complexity again is in this search. This is the exponential part, is on the k. And then we have the polynomial in n for accounting for producing the reductions, okay? And we get that it's fixed parameter tractable, okay? And since I ran out of time, I will not explain the other result, which I think this is more interesting anyways, So, thank you.
Time for 1 or 2 questions.
Is there a continuous generalization for this?
What do you mean by a continuous?
Continuous, because this is a discrete problem. It would be interesting to know whether this is simply connected, if it would be continuous.
I don't know.
Good topic for discussion. good to discuss over lunch, I think. Yeah. I have one quick question. Do you think this reducing you 2 to 1 will eventually go to 0?
Well, we thought about that a lot, Catherine and I, and I think we've come close, but we cannot manage to do anything else so far, And part of why this is so difficult is because the SPR distance doesn't have the forest characterization to work with. And we try to do a characterization of the distance instead of in terms of the forest, as the TBR or rooted SPR distances have. And we worked very hard and couldn't get it. So I don't know if somebody wants to discuss, I can explain the result, and maybe somebody has some ideas, how to remove this +1, parameter. We don't know how to do it. And we've worked very hard,
With much more than $100. Okay, let's thank Maria.